So I'm going to make a video about the transition maps for a vector bundle and its dual. So let's recall some things. So let's let X be a scheme. And let's let F be a locally free sheaf. Sheaf on X. And then this means is that there's going to be a cover. So there exists a cover. Such that F restricted to UI is isomorphic to something of rank R. So the structure sheaf of rank R restricted to UI. We can call this phi here. Okay, and so because of this, we know that we can compose this with its inverse. So we have the following. So what we have these maps phi j, and so this is going to be defined to be phi composed with phi j inverse. And this is a map from OR of Uij to OR of Uij. So this is an isomorphism. This is an isomorphism here. Okay, and so this is actually will be, since this is a morphism of O modules, or O of X modules, right? So this is the structure sheaf of X. This thing is a matrix, so this thing will be a matrix. So phi j acting on some here, we'll view it as a column vector E will be equal to A, and then we're going to write the superscript here like this, times E. And so we'll view this as a column vector. So elements of this thing will be viewed as column vectors, and this is a column vector here. And then this thing here is matrix multiplication. So this is a matrix, and so this is an element of GLR of O of Uij. Okay, so this is what the transition maps look like. So this is these are the so-called transition maps. Okay, and what we do is we get from this we can get a cohomology class. The class of this locally free sheaf, which sits in H1 of X. So this is check cohomology really of, and then we have GLR. Okay, so this is the cohomology class associated to locally free sheaf. And so the question that I wanted to answer and that I'm going to use is what are the transition matrices for F dual, which is, we'll say this is Hom of F into O. And so this is the dual locally free sheaf. So this is the dual locally free sheaf, okay? This is the question. Okay, and then so the answer is the following. I'll call it a theorem, but it's really not too big of a deal here. It says that with Uij being the same open cover, and let's say with the same setup, and let's say the transition matrices for let's say F dual are the following. So we take Aij, we're going to take the transpose of it, and then takes the inverse. It actually doesn't matter if we do transpose and inverse. So let's make a little remark here. Note transpose and inverse commute. Okay, so let me give kind of the setup so we can prove this. So locally, so locally, so this is say on an open set. So let's say if V1, VR are a basis for F, then let's say V1 dual up to VR dual are a basis for, let's say, F dual, such that, well, we can take VI and apply it to some VJ, since they're HOMs, and so this thing will be 1 if I is equal to J, and 0 if I is not equal to J. In other notations, we will write this as VI star VJ, so we'll write this like this. Okay, now we need to make sense of what locally means, and by this we mean on the set, okay, on the set UI, so we're going to fix this cover like we did before. We're going to set, well, the inverse image of the elementary row vector, so this is this, and then let's call this L here. And so this is the elementary elementary column vector. This will be defined to be equal to VL, and then we'll write an I here. Okay, so this will be a basis. So so this means that V1I, and this, we'll say this vector bundle has rank R, VIR is a local basis. Okay, so this is what gives us our trivialization. So this means we can define take let's say VI so say V1I dual up to VRI dual to be a basis for let's say F hat restricted to UI. Okay. So with this, we define phi, the trivialization here for F restricted to UI to O of O restricted to UI. And this is to the rth power, and this is given by sending these VLI duals to these elementary row vectors. So this will be EL, or sorry, we'll say elementary column vector. Okay, so okay, so this the trivializations respect the pairing. Okay, and by this we mean that if so for V in F and V, let's say W sharp in or W star in the dual, then for each I, and so for all these, and all i's, then phi here of W sharp is going to be equal to phi of V. Okay, and this is just going to be W star V. Okay, and what do we mean by this thing? Where W star of this thing is defined to be equal to, shit, sorry. So this thing is now an element of here, okay? Where this thing here, where for, let's say, xy, an element of O to the r, xy is defined to be equal to x transpose times y. And so now this is taking a column vector, turning it into a row vector, and now this is a column. Okay, so this is the usual dot product. Okay, so so it remains to compute. So we've just done all this stuff here just to set up the situation. Okay, so we did everything. We talked about all these things just so we could talk about a dual basis now that we have enough words to do the local computation. So now we compute. So we do the now we compute. So we're going to compute phi ij star. And so this is going to be phi I star composed with phi j star inverse. Okay, and we want to just see what this thing looks like. Okay, and to do this, well, what we're going to do is we're just going to take, so we'll just do it for elementary column and row vectors. So here, so phi ij star applied to EL. Okay, we'll suppose that this thing, it looks like some matrix, but we'll just take K here. Okay, so by this thing that we said that the pairing is respected, this part here, this thing has to be equal to EL EK, and this is just the Kronecker delta. Okay, and now this thing here, we're going to write this just as a matrix. So this will be Bij, and this is what the translation matrix looks like. This is matrix multiplication, and then here, and then we had Aij of Ek here. Okay, and now we write out what the definition was using this thing. So this is equal to Bij El transpose of Aij Ek. Okay, and now now this is equal to, so we'll just write it out. So this is El transpose of Bij transpose of Aij Ek. Okay, and so now we have an identity. The identity that we have is that El transpose Bij transpose Aij Ek is equal to the Kronecker delta DLK. Okay, and so this is equal to this part here. So this is the lth row of Bij transpose, and then this thing here is the kth column of Aij, this matrix Aij. And now, so the lth row, so this lth row times this kth column gives this is equal to the, this whole thing is equal to the LK entry of the matrix Bij transpose times Aij. Okay, and so this is equal to this identity. So this implies that well, Bij transpose times Aij is equal to the identity. So this is the R by R identity, which tells us that Bij transpose is equal to, well, just Aij inverse. Okay, and now this the rest follows. So now so the theorem follows from this. So follows from this. Okay, and so now we've essentially shown how the matrix of so that the check cohomology class associated to a vector bundle and it's dual related, and that's by inverse transpose. Thanks for watching. Bye.